Audible?
Yes, sir.
Okay. Am I audible now?
Yes, sir.
Yes, sir.
Okay, so uh, yeah, so last time what we are doing, we have discussed about the Cantor distribution, right? Um, yeah, so this is the density function. We have this thing, and this is mainly for the continuous distribution, and yeah, we will continue. So, and yeah, so what we have done is the probability of x belongs to B is nothing but integral over B if x, this is and if x is the density. And uh, and for this is for the continuous thing, and for the discrete thing is just the sum, right? I mean, it's like summation and um, summation. I mean, this is So this is for the discrete. So this is for the discrete thing, discrete random variable, and this is for the continuous random. Continuous random variable. And we know that distribution function which has density is called the it's called absolute continuous distribution. And yeah, and we have also look at these things. I mean, we have also um, seen that the distribution function is from the it's like fx6 x is equal to minus infinity to x fx6 dx. Right? And this is also we write it as probability of x less than equal to c. This is the distribution. And now, so naturally, I mean, there is also the natural thing is um, um, so suppose x is a continuous distribution. Continuous distribution with density of x. Know that we show that the derivative of these things is so 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 when uh, continuous values. So I mean the density function is so in a sense that so it's quite natural, right? If you see that fx definition as this integral, I mean, then I don't think it's very hard to pull. It will not be that. It will not be that difficult to show this. That, because sorry, I just did a mistake. Sorry, I think I've done little mistake. Yeah, I was doing one mistake here. So so you see, this is fx. So minus it. So here is the x. So I mean, this fellow should be different variable, right? I mean, otherwise, so it is fy dy. So yeah, similarly, it is because otherwise it does not make sense, correct? I mean, because the variable has to be minus infinity to x. So it is, yeah, so yeah, so this mistake I did. So similarly, it will be here is also I have done a mistake. So this is this will be I don't know. Yeah, so it will be fine. Yeah, the moment you write it that way, then it's not a problem because it is the so in a sense that if you have I mean if you write fxx is equal to minus infinity to x fy dy, right? And fxy dy, and what you have given that this is continuous function, right? Fx is a continuous function, then therefore you can do the differentiability because it is given to you that this is continuous at least, right? So if you have a continuous function, you do the differentiation both side, ddx of fx of x, and then this is nothing but this fundamental theorem of calculus. You just this is fx of x, right? This is the fundamental. I mean, you can do one more, right? Is you can write ddx of minus infinity to x fx of y dy, and by fundamental theorem of calculus, this is nothing but the fx of x. I think this is the fundamental theorem. There is nothing that um, yeah. Okay, so now we'll do something called joint distribution. So it's called the joint distribution. Mm. So join. So yeah. So in a sense that uh, so we have done what is called this is the this is for single these things. So single random variable, right? I mean uh, single random variable. Now we are looking for joint distribution for for I mean this was over a real line over R. Now we are looking something over R2 or R3 or Rn. So joint distributions, joint distributions of mm, of random variables. And is a probability measure. Okay. One Rn. This is over Rn. Is that or so is that for any Borel set over Rn. Uh, Probably x1, x2. So you see, so this is nothing but joint probability based. So joint distribution comes with joint probability. So this is multivariable. I mean, it's nothing this thing. And if you have a uh, so if you have a this thing, if you have uh, a Borel function, Mhm. this one. So the dense distribution. So what we have done earlier for one dimension, this is correct. So small dx1 dx. I mean, this is nothing but just the multivariable thing. I mean, this and this. I mean, the same thing, right? I mean, this probability of x belongs to b integral over b fx dx, and here x1, x2, xn. Uh, so this is a yeah, this is a random variable. You can just you can consider it as one way. You can write it as actually vector. That might be better to write. So it's a vector. I mean, this is a vector in dimensional vector. So similarly, if I just write it here, just write it as vector. And this is a function from Rn to R, so real valued function. This thing and this is R. So fx f such this one is a Rn to R. So this is this one to this is joint density of x1, x2. This is joint density. Now, why I did this, we will use this multivariable, these things later. Not, I mean, for the time being, not now, but I just wanted to introduce this thing because we were introducing distribution, density, all these things. So, yeah, we will use this little bit late, but it does not matter. I just wanted to do it together because and okay, so another important concept is is called the expectation of random variable. So expectation of random variable is this is for continuous random variable is as x omega dp. And so this is the expectation of random variable for continuous random variable. In some places, it is just simply write it as omega x dp. I mean, this small omega, which is belongs to this. Sometimes they keep it as auxiliary. Okay? It is, I mean, because random variable is always a map from capital omega to R, right? Yes, yes, this is a function of small. I mean, small omegas are sample points of the sample space. So many places it writes just for convenience is x dp, but basically it is like nothing but x omega in dp omega. So the integration with respect to the probability measure. Expectation is nothing. The integration of the random variable with probability. But yeah, as it one condition is required is provided. So this definition holds provided uh, integral x omega, this is modulus dp omega. I mean, you can write with small omega, whatever is finite, provided this is finite. So this condition is required to have the to define the expectation. I mean, this is nothing but integrability condition, right? So the expectation exists, or I mean, otherwise it's infinite. So if you have an integrable condition, if this integral is finite, modulus of x omega dp omega, then we define expectation as this, because this is nothing. So integrability condition. And uh, yeah, so this is yeah, basically this is integrability condition. And sometimes this the space of or space, or it's a family of a family of integrable random variables omega to r is denoted by L1. L1 is called L1 functions. Or simple, or in short, you can just write L1 also. In some book, it is just simple L1, this one, or some book, this is also written as script L1. Okay, so I mean, it's so some book it is written as script L1, some book it is just simple L1, whatever it is there. But this family is the family of integrable functions is called this. Okay. Now another thing. So you know what is indicator function, right? Indicator. So what is an indicator function? Indicator function is, so this is 1 if omega belongs to A, and this is 0 if omega is not. Okay. So this is the definition of indicator function. And this A is a event, so this is the definition of indicator function. Okay. Now, what about the expectation of indicator function? What about this? So this is, if I write the definition, correct? This is my definition, right? Now, now this is, I mean, for any omega, how can you write it? A union A complement, right? You can just write it simply this way, right? Correct? Yes? Hello?
Yes, sir.
Any omega, you can write it this way, right? So, so basically, this one you can, this integral, you can simply write it as integral over A, right? Plus integral over A complement. And this is disjoint. A union A complement is disjoint. So this is, you can write it as a. Now when omega is in A complement, so omega is not in A means omega is in A complement. So then this part goes to 0, right? This part does not make sense. I mean, if omega is in A complement, because this integral is over A complement, this part goes to 0. And this is just simply 1. This is 1. So in a sense, that this is integral over A 1 into dp omega, right? And so integral over a set dp omega, this is nothing but probability of. I mean, integral over A into dp omega is nothing but the probability of A, probability of that set. So expectation of indicator function over a set is nothing probability of this. And yeah, so this is the for the indicator function, and another is called the step function. We can have a step function. Step function is what is so say, I mean, it's a function. So, so it's a step function. So suppose G is a function. Okay, G is a function from omega to R. I mean, I'm taking omega to R. It's step function if so G omega to R is a step function if we can write G as summation I equal to 1 to n Gi indicator of AI. So in a sense, how, or you can say more, I mean, Gx, you just leave it. And you can write G of omega, some because it's omega from this I equal to 1 to n Gi of omega indicator of AI of omega. This is much precisely. So in a sense that so 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 this is, it will be G1, right? G1 of omega if omega belongs to A1, because otherwise it is 0. It will be G2 of omega if omega belongs to A2. It is Gn of omega if omega belongs to An. So in a sense that if you draw the function, so x-axis, this is y-axis, right? So suppose I divide, yeah, so AI is a disjoint I have taken. So if I take, this is A1, this is A2, so A1, A2, right? This is something AN, right? So G1, so its value is something G1 at A1, G2 at A2, suppose G3. So this is my G1, G2, G3, dot 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 something somewhere, whatever it is. So sorry, we can have, so here it is Gn. So, so here it is Gn. So basically this is steps, right? I mean, this is step. I mean, that's why it is called step function, because I take constant in each of the interval. I take constant in each of them. So so AI is the disjoint, that is important. AI intersection is AG is equal to disjoint. And GI is, these are real numbers. So because this is a map from, so in a sense, GI is also a map from capital omega to R. So some real numbers. Now, if I have a step function, what about the expectation of G? Right. So you can write more precisely at G omega, that is also fine, right? So I just write what is the definition of G omega. I equal to 1 to n Gi omega indicator AI omega. Right. Correct. And what about, what is mean by expectation? Expectation is nothing but the integral over omega. So this is I equal to 1 to n Gi of omega indicator AI of omega. Okay. I just sorry, I just did a one mistake. Mm. So so G1, G2, GI are so this is the value, right? This is not random. This is value. So so in a sense, I did a mistake. So GIs so so GIs you see GIs are values. So GIs are real numbers. So it will GIs are values because I mean in A2, sorry, in A2 this is G2, in A3 this is G3, right? In AN this is GN. So GN is the value, right? So yeah, so sorry, this is my mistake. So in a sense the it's nothing. The omega will not be here. Just so mm, yeah. So expectation is nothing but DP. This is the definition of expectation, right? And or even you write this step, or even we don't need to write this step. You just can write. You cannot write whatever. So, just, let's keep it simple. And so this is this thing. And expectation is linear, and here the sum is 1 to n. So I can take the expectation inside, and this is constants. I mean, this is GIs are real numbers, right? So 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 we can write this uh, that GI belongs to for I equal to 1 to. So GI belongs to R. So therefore, expectation will go inside because it's a constant indicator AI of omega. And this one we have already seen. What is this, right? I mean, this is nothing but indicate expectation of indicator is nothing but the probability of it. So this is this is okay. ठीक है. Any question?
No, sir.
Yeah, so for the step function, this is the expectation you calculate, and for the indicator function, this one and the step function. So we need all these things later. Okay, so see you on Monday. Okay,
Okay, sir. Thank you, sir.
thank you.